Unpacking the Sun's fury, the Coronal mass ejection and its impact on Earth. Two powerful solar flares headed toward Earth. What happened? On April 19, NASA made an announcement that two strong solar flares had erupted from the Sun and were headed towards Earth. These flares reached their peak at 9:35 p.m. and 11:57 p.m. ET, respectively, as observed by NASA's Solar Dynamics Observatory. Solar flares can last for a few minutes or even hours and can affect everything from the electrical grid to radio communications and navigation signals. They can also be dangerous for astronauts in orbit. The worst part is that the harmful electromagnetic radiation travels at the speed of light, so by the time we see a flare coming, it's already here. Solar flares are one of the most powerful and fascinating phenomena in our solar system. These intense bursts of radiation and particles from the surface of the Sun can have significant impacts on Earth's technology, infrastructure, and even our daily lives. Understanding the science of solar flares, their connection to Earth's magnetosphere, and the potential consequences of a major event is crucial for predicting and mitigating their effects. In this article, we will explore the science of solar flares, the role of the Sun in their formation, ongoing research by NASA, and the potential risks posed to Earth. The science of solar flares. What are they and how do they affect Earth? Defining solar flares and their characteristics. Solar flares are bursts of high-energy radiation that originate from sunspots, which are regions on the Sun's surface that have strong magnetic fields. These flares can release as much energy as 1 billion atomic bombs and can last from minutes to hours. Solar flares are classified according to their X-ray brightness, and their energy output ranges from a few joules to over 10^32 joules. The most powerful solar flares can also trigger other solar phenomena, such as coronal mass ejections (CMEs) and geomagnetic storms. The interactions between solar flares and Earth. Solar flares can have several effects on Earth's environment. They can cause disruptions in radio and communication signals, affect the power grid, and even cause auroras to appear in the sky. The charged particles from a solar flare can also interact with Earth's geomagnetic field, creating a geomagnetic storm. These storms can last for several days and can cause further disruptions to communication systems and power grids. Although solar flares and their effects can be harmful, scientists continue to study them to better understand the Sun's behavior and to protect Earth from their harmful effects. The role of the Sun in solar flares. Understanding the source of this powerful phenomenon. The structure and function of the Sun. The Sun is a massive ball of gas, primarily made up of hydrogen and helium, that generates energy through nuclear fusion in its core. This energy is then released as light and heat that radiates out into space. The Sun also has a complex magnetic field that plays a crucial role in the formation of solar flares. Sunspots are regions on the Sun's surface where the magnetic field is particularly strong, and they are often the origin point of solar flares. The processes that lead to solar flares. Solar flares occur when the magnetic field lines in sunspots become twisted and tangled, releasing a large amount of energy in the process. The energy is released as high-energy particles and X-rays that can travel through space and have an impact on Earth. Scientists continue to study the processes that lead to solar flares, with the goal of predicting them accurately and mitigating their effects on Earth. NASA's ongoing research. Monitoring and predicting solar flares and geomagnetic storms. The tools used to study solar flares and their effects on Earth. NASA uses several tools to monitor and study solar flares and their effects on Earth. One such tool is the Solar Dynamics Observatory (SDO), which captures high-resolution images and data of the Sun's atmosphere. NASA also has a satellite called the Advanced Composition Explorer (ACE), which monitors the solar wind and helps predict the onset of geomagnetic storms. The importance of accurately predicting solar flares and geomagnetic storms. Accurately predicting solar flares and geomagnetic storms is crucial for protecting Earth's communication systems and power grids. Researchers and scientists continue to study solar flares and their effects on Earth, with the hope of being able to predict them more accurately in the future. The impact of solar flares on Earth's magnetosphere and power grids. The mechanics of geomagnetic storms and their effects on Earth. Geomagnetic storms, which are caused by the interaction between solar particles and Earth's magnetic field, can have several effects on Earth's environment. They can cause power outages, disrupt satellite communications, and even pose a health risk to astronauts in space. The risks posed to modern technology and infrastructure. As our technology and infrastructure become more advanced, the risks posed by solar flares and geomagnetic storms become more significant. It is crucial that researchers and scientists continue to study these phenomena to better understand their impact and to develop more effective ways to protect our modern technology and infrastructure. Coronal mass ejections. How they differ from solar flares and their consequences on Earth. Defining coronal mass ejections and their characteristics. Coronal mass ejections, CMEs, are massive eruptions of plasma and magnetic fields from the Sun's corona. They typically occur in conjunction with solar flares, but they are two distinct phenomena. CMEs are more massive and slower moving than solar flares, and they can contain billions of tons of matter, which can take days to reach Earth. When a CME hits the Earth's magnetosphere, it can cause a geomagnetic storm, which can disrupt satellite communications, power grids, and other technologies that rely on a stable magnetic field. The similarities and differences between coronal mass ejections and solar flares. Solar flares and CMEs are both caused by the interaction between the Sun's magnetic fields and its plasma. However, while solar flares are sudden, brief bursts of high-energy radiation, CMEs are slower moving and more sustained eruptions of plasma and magnetic fields. CMEs are also potentially more dangerous than solar flares because of their mass and the longer periods of time they can affect Earth's magnetosphere. Both solar flares and CMEs can cause auroras, northern lights, when they interact with Earth's atmosphere. Magnetic fields and solar flares. Exploring the connection between the Sun, Earth, and space weather. The role of magnetic fields in the formation of solar flares. Magnetic fields play a crucial role in the formation of solar flares. The Sun's magnetic fields can become twisted and distorted, leading to the buildup of energy that is eventually released in the form of a solar flare. This process is known as magnetic reconnection. The energy released in a solar flare can be equivalent to billions of atomic bombs, and it can produce high-energy radiation that can affect Earth's atmosphere and disrupt satellite communications. The interactions between magnetic fields and Earth's magnetosphere. Earth's magnetosphere protects us from the harmful effects of solar radiation and charged particles. However, when a CME or solar flare hits the magnetosphere, it can cause disturbances that can lead to geomagnetic storms. The magnetic fields of the CME or solar flare can interact with Earth's magnetic field, causing it to become compressed and distorted. This can lead to disruptions in satellite communications and power grids, as well as the creation of auroras. Preparing for the next solar flare. Steps taken to protect technology and infrastructure. The importance of developing effective mitigation strategies. As our dependence on technology continues to grow, the potential effects of a large solar flare or CME on our infrastructure become more significant. To prepare for such an event, scientists and engineers are developing mitigation strategies, such as building stronger power grids, developing backup satellites, and improving forecasting of space weather. These strategies are crucial for minimizing the potential damage caused by a solar flare or CME. The potential consequences of inadequate preparation. The potential consequences of inadequate preparation for a solar flare or CME could be significant. A severe geomagnetic storm could disrupt power grids, leading to widespread blackouts and the loss of critical infrastructure. Satellites that provide communications and GPS services could also be affected, leading to disruptions in air travel and other critical services. It is therefore essential that we continue to improve our ability to predict and mitigate the effects of space weather. Future studies and discoveries. Advancements in solar flare research and their implications for space exploration. New technologies and methods for studying solar flares. Advances in technology are allowing scientists to study solar flares in unprecedented detail. New telescopes and spacecraft are being designed to capture high-resolution images and data from the sun's corona, allowing us to better understand the mechanisms behind solar flares and CMEs. Machine learning algorithms are also being used to analyze the vast amounts of data produced by solar observatories. The role of solar flare research in future space missions. Understanding the effects of solar flares and CMEs on space weather is crucial for planning future space missions. Solar flares can produce high-energy radiation that can be harmful to astronauts and spacecraft. By studying solar flares and their effects on Earth's atmosphere, we can better prepare for missions to the Moon, Mars, and beyond. Additionally, studying the sun can help us understand the origins of life on Earth and the formation of our solar system. In conclusion, solar flares are a fascinating and important part of our solar system. As we continue to study and understand this powerful phenomenon, we can better prepare for their potential impacts and mitigate any risks they pose. With ongoing research and advancements in technology, we are well positioned to continue learning about solar flares and their implications for our planet and beyond. FAQ: What is the difference between a solar flare and a coronal mass ejection? Solar flares and coronal mass ejections (CMEs) are related phenomena, but they are not the same thing. A solar flare is a sudden, intense burst of radiation and particles from the sun's surface, while a CME is a massive cloud of charged particles that erupts from the sun's corona. While solar flares and CMEs are both caused by magnetic activity on the sun, they have slightly different effects on Earth's magnetosphere and technology. Can solar flares affect human health? While solar flares can have significant impacts on Earth's technology and infrastructure, they do not pose a direct threat to human health. However, in rare cases, astronauts and airline crews flying at high altitudes can be exposed to increased levels of radiation during a solar flare event. NASA and other space agencies closely monitor solar activity and take measures to protect astronauts and other personnel from any potential harmful effects. How do scientists study solar flares? Scientists use a variety of instruments and tools to study solar flares and their effects on Earth. NASA's Solar Dynamics Observatory and other spacecraft provide detailed images and data on solar activity, while ground-based observatories and networks of magnetometers track changes in Earth's magnetic field. Computer models and simulations are also used to predict and understand the processes that lead to solar flares and geomagnetic storms. Can we predict when a solar flare will occur? While scientists have made significant strides in predicting solar flares and geomagnetic storms, it is still challenging to accurately forecast when and where they will occur. However, NASA and other agencies continue to invest in research and technology to improve our ability to predict and prepare for solar activity. In the meantime, it is important to have effective mitigation strategies in place to protect our technology and infrastructure from the potential impacts of a major solar flare event.